All right. Well, I was gonna do a big video on Kepler's laws, and then decided, I should really break it up into about four little videos. So before we jump into Kepler's laws themselves, let's talk about where Newton's law of gravitation come from. I mean, of course, if you have taken physics, you know it should look something like GMM over R squared, R hat, so this is the unit vector, and a minus sign because it's attractive. So that's the force between two objects, the gravitational force. But you might have wondered back, I don't know if you wondered this back in physics or not, how did Newton never come up with this? Because gravitational force is very small. Right? I mean, we have one particular object that's big enough and that we're living close to, the planet Earth. And we can presumably measure how strong is the gravitational force between Earth and an object. But the thing is, that object is at least going to be the radius of the Earth away. So how can we possibly measure this precisely enough to figure out that it's an inverse square? Well, the answer is we didn't get this by measuring. So Newton didn't measure this. Where he wound up getting it from was from Kepler's laws. So it's going to be a little bit roundabout, but what we're going to see is that what Newton did, he assumed that Kepler's third law was true for a circular orbit. And you might ask, well, why can he assume that's true? Well, physics has to come from somewhere. I mean, ultimately, we can't just logically deduce what the laws of the world are. We have to actually measure something and then come up with a principle from it. And so that's what he did. He said, well, if you know the history of it, there's I don't remember how Tycho Brahe.
Tycho.
Tycho. Thankfully, my
Brahe.
Thankfully, my wonderful spelling wife is sitting beside me. She can tell me how to do these. Basically, he took 20 years of measurements of planetary orbits, and then his protege, Kepler, he studied those notes for 16 years. So he took 20 years of measurements. Kepler looked at them for 16 years, and he came up with his three laws based on that 20 years worth of data. So that's where Newton was coming from. He said, well, according to all, I mean, if you want to really study gravity, you kind of have to go with celestial bodies because they're the only things big enough to really have a chunk of gravity between them. I mean, if you just talk about the gravity between me and you, I mean, it's something so small you'll never measure it. And so if you look at the notes from the two guys who wrote the definitive measurements and definitive laws on celestial bodies, I mean, this is what it looks like happens. So he assumed Kepler's third law was true for a circular orbit. And from that, he got the law of gravitation. So the logical chain is third law for circles implies Newton's law of gravitation. And the law of gravitation implies all three of Kepler's laws, even when the orbit's not a circle. So in this video, we're going to talk about this first implication here. How, if you assume the third law for circles, you wind up getting the law of gravitation. Okay. So a circular orbit is pretty nice because one thing that's very different about a circular orbit is just because of symmetry, if you want to just think from a mathematical standpoint, or if you've taken some physics, this is from the conservation of angular momentum. But the nice thing is, whichever way you think about it, is that the speed is constant. If you're moving in a more complicated orbit like an ellipse, we'll see later that you slow down on this outer edge and you speed up as you get closer to the planet. But for a circular orbit, just symmetry's sake, it should be obvious that if you've got an orbit going on, you're going around at constant speed. It would seem really strange if I was going, then all of a sudden I sped up and then slowed down, sped up. Yeah. Okay. So that's one thing nice going for it. And what Newton and other physicists already had done is he had already derived the centripetal acceleration, which we saw in physics, and we have also seen it in this class now, that the acceleration when you're going around in a circle is v squared over r, right? Okay. So to this, we add Kepler's third law. So Kepler's third law says that the cube of the mean distance, so for a circle, there's just going to be the radius, but in general, this is the major semi-axis of an ellipse. But anyway, we're just saying Kepler's third law is true for circles. So anyway, the cube of the radius should be directly proportional to the square of the period. Okay, and so k is just some number. This could depend on the two bodies or whatever, but it's just for any particular bodies, there's some number that makes this work. And now Newton just took these two equations together, and from that he got the law of gravitation. So let's see how that works. Well, first of all, what is your period going to be? I mean, period is the length of time it takes. Time is distance divided by speed, right? So the distance around the circle is 2 pi r, and speed is v. So if I plug that in here, I've got r cubed is proportional. So that'd be 2 pi squared, r squared over v squared, right? And what I really care about, I'm looking over here at my acceleration formula. I would like to know about v over r, or sorry, v squared over r. So if I move the v squared over and move 2 of the r's over, or sorry, no, I need to move all 4 over. So I would have v squared over r. So I'm multiplying both sides by v squared, dividing both sides by r to the 4th. That'll give me an over r on this side. Would be k times 4 pi squared. And then the v squared will cancel. And then this is over r squared. So we get the acceleration looks like something times 4 pi squared over r squared. So in particular, it has this inverse square thing. Well, what about force then? Well, so I've got this big mass in the middle, little mass on the outside. I know the acceleration of the little mass on the outside is given by this. So the force should be just acceleration times mass, right? So mass and then k 4 pi squared over r squared. So this is just some constant. Okay. And then kind of we add together Newton's third law. Well, that's the force on the little guy, the force on the big guy, by the same reasoning. I mean, I think about the little guy going around the big guy, but if I was setting on the little guy, it would look like the big guy was going around the little guy, right? So I could use the same argument to get the force on the big guy is M, and then this same K, and then different K. All right. And so, and of course, these have to be equal. So we get altogether the force is directly proportional to both of the masses, and it's inversely proportional to the distance squared. So altogether you have, well, it's directly proportional to the two masses, inversely proportional to the distance squared, and then so there's just some proportionality constant, and then r hat. So that is how Newton got his law of gravitation, was by assuming Kepler's third law was true for a circle, and then he used that to say, well, as we know just from second law of Newton's, that it has to be directly proportional to the masses, and then Kepler's third law gives you the important inverse square factor. So that's how he got his law of gravitation. And then we'll see in the next 3 videos, once we know the law of gravitation, how do we get Kepler's 3 laws?